great. I'm super happy to be able to introduce Dr. Michael Rowe from University of Auckland in New Zealand. And two people have asked me how I know you, and I don't know how we met, but we didn't even overlap. We had the same advisor, and he probably had something to do with it. Yeah. Let's see, Mike started at Washington State University, and then stayed there, and then went to, not stayed there, but like stayed there for a little while. And then went to Oregon State University, got his PhD there, and then has done research positions in Ohio, UT, no, Iowa. It's the same vowels. It's not even the same vowels. Anyway, it's not on the West Coast. That's what it has in common. And then has been in Auckland since 2013?
Yeah.
Something like that? Yeah. So Mike and I met up over the summer, and I talked him into coming up to Chico on his way, not on his way to San Francisco.
Relatively speaking, it's on my way.
There you go, yeah. For all intents and purposes. And then next week we'll be at AGU. So, take it away.
All right. Yeah. No, I'm happy to be here. So, I guess a little bit about my background. I'm primarily an analyst by nature. My early training was on electron microprobe and laser ablation and running those facilities. In fact, that was my last position before going to Auckland in 2013. Was I was running the field emission microprobe and X-ray diffractometer in that lab. So I consider myself more an analytical geochemist anymore, rather than strictly an igneous metrologist and volcanologist, although most of my work you'll see is still in that petrology realm. But I mean, what I enjoy doing anymore is problem solving for geochemistry. So I use a wide range of different equipment, and it gets me into a bunch of different projects. After AGU, for example, I'm off to go to Japan for a planning workshop for returning samples from Mars. And last week I was in Sydney looking at early life in drill core sort of stuff. So it's a wide range of different applications. But today we'll focus on using kind of the mineralogy and geochemistry, looking at volcanology and volcanic hazards. Bit about the talk, so I'll give a bit of an overview on the Auckland Volcanic Field and phreatomagmatic eruptions in particular. The key questions that I'm hoping to address and the methodology, just a little bit about what I found. I'll try not to show too many geochemical plots. And then, just because I was feeling ambitious or sleep deprived, added in a little bit of a comparison to some work we're also doing in Vanuatu using similar techniques and looking at the same sorts of problems. There we go. Oh. There we go. All right. Trying not to step in front too much here. All right, so the Auckland Volcanic Field. So this is going to be urban geology at its finest. So the Auckland Volcanic Field has around about 52 different volcanic events that have been identified. So the main downtown for Auckland sits here, and I'll show you a population map a little bit later. But this shows the distribution of volcanoes kind of throughout the field. We're not talking about a very large area here, but you can see we get quite a distribution of basaltic lavas, tuff rings, scoriocones, all distributed through these kind of high-density urban areas or suburban areas. It's also a relatively young lava flow, or a lava field, from about 190,000 years up until present. The most recent eruption was about 500 years ago. And that also happens to be the largest there with Rangitoto. Given its setting here, you can see we've got a lot of water around, and as a result of that, we get a wide range of volcanic eruptions. So you get Mars, you get tuff rings, cinder cones, lava flows. A lot of the styles of eruption all come down to how the magmatic system has interacted with water, either subsurface or seawater here. And we'll talk about some examples here in just a couple minutes. Some of these centers have had multiple styles of volcanic eruptions, and that's kind of what I'm going to focus on today, is how the eruption style changes either through interaction with water or changing properties of the magma system. But it's very common to start off with a phreatomagmatic eruption where you're having a lot of magma-water interaction, and then transitioning to a classic Strombolian style eruption where you're building up cinder cones and you get your effusive lava flows. I'm just going to put that down. Again, just showing the relationship to the population here. So Auckland right now sits at about 1.5 million, which I guess for California is not terribly huge. For New Zealand, that accounts for about a third of the country's population. So it has an eruption in this area will have a significant impact on the economy and the population as a whole. Again, still superimposed. Ignore the stars; those are some of the volcanoes, but these are all, again, the volcanic centers. And I should point out, again, Auckland, situated on the North Island here, kind of on the Northland area, the north tip of the island. And as you can see, we've got the Tasman Sea on one side on the left and the Pacific Ocean there on the right. Okay, so in terms of some of the different volcanic systems we have, this is kind of a classic example of one of these eruptions that transitions from a phreatomagmatic system, so a strong water-rock interaction, to a Strombolian or a drier system. So this is Motokorea. It erupted about 14,000 years ago, so it was a period where we had kind of lower sea levels. It's an isolated island now, and it was more isolated at the time of the eruption. And you can see in the upper photograph we have a nice scarp here, and I'll show you a zoom in on that on the next slide. But this is one of part of the tuff ring here that forms this northern side of the island. To the south and to the west are the lava fields, and then right in the middle is the scoria cone. That's kind of the last stage of the eruption. So again, this started out as a wet system, forming the tuff ring around the margins, erupted the lava flows that make up kind of all this portion, and then the scoria cone at the top. Fieldwork here is fun. The only way to get there is by taxi. So it's not a heavily populated island, and it's a nice boat ride out there, but again, urban geology. So this is the section of that cliff face, that sea cliff that I showed in the previous diagram. And this again is classic for these phreatomagmatic eruptions. You get alternating layers of, you can see it as a light color here, and then some darker bands throughout it. So these lighter layers represent our volcanic ash and a lot of the fine-grained sediment from phreatomagmatic explosions. You get certain thicker layers through here that represent more scoria-rich deposits, sometimes from jets or even sometimes from some Strombolian-type eruptions kind of interspersed throughout. But you can see you get a lot of individual discrete events associated with this style of eruption. So if we look at that with stratigraphy here, so this section is about 20 meters thick here, and you can see from the stratigraphic column there are a lot of different individual eruptive units throughout this tuff building phase. A couple in particular note that we'll come back to is what's referred to as this middle scoria unit and that upper scoria unit. So we'll look at those in more detail here in a few minutes. So in terms of the model that's been proposed for how this system evolves, you get the injection of magma into the shallow subsurface here. And this is where this interaction with groundwater becomes important, and we get what's referred to as fuel coolant induced fragmentation here. Basically, we flash the water to steam and we cause explosions. So these tend to form an excavation here of that subsurface, and we get these craters drilling down into the substrate. So when we look at those sections of stratigraphy, a lot of that fine ash is actually simply pulverized basement rock and not necessarily juvenile magmatic material. Now, as this eruption progresses, you can see from the illustration here, we blow out the basement material as well as some of that juvenile material, and this starts building up the walls of this tuff ring. Now this material tends to be wet, it sticks together, and it makes fairly resistive units, much more so than what you see with kind of the classic scoria cones where you get material that just easily erodes off the sides. So this eruption progresses, and what's been proposed here is that basically the system starts to dry out, either, well, in this case, simply by drying out the area around the vent, and then transitioning then from kind of these steam explosions to the cone building phase, at which point we now move into kind of this Strombolian style eruption. And so we get the eruption of the lava flows and your cinder cone here in the middle of the system. So this is just the view from the cinder cone at the top, looking over at Rangitoto. So that'll be the next one we'll look at. So Rangitoto is a classic shield volcano. You can see the nice gentle sloping sides. And it's then topped with a scoria cone. Actually, technically there are two, but one prominent scoria cone kind of right at the top of the mountain here. So Rangitoto is the only subalpine volcano in this entire volcanic field. So it's got a slightly different composition. It's also volumetrically significantly larger than everything else. So we get a large amount of mantle melting, gives us a different composition, more magma being produced, bigger lava field, and in some regards very different style of eruption from what we see in these kind of phreatomagmatic and Strombolian style eruptions. It's also the youngest, which makes it a great interest to civil defense, because this is what everyone looks at for potential future eruptions. Again, it erupted last about 500 years ago, but also may have had an earlier phase that was at about 1,000 years ago. There's still some debate around the time of these eruptions. What I want you to also take from this is the joys of working in a very warm and humid environment for fieldwork. So this is the youngest system we have to work with. And this is the absolute best outcrop we have found up near the scoria cone. Luckily, there's a trail that goes up by it, and that's why we have the outcrop here. But most of it, if you're trying to work through it, is just kind of dense bush. But this is actually a nice fresh outcrop of scoria, so it makes it good for doing this sort of work. So the view here is looking back towards the city center of Auckland. And I've identified two of the other volcanoes that I'll talk about here. Mount Eden, and kind of a bit further away there, is one of these Strombolian cones, and North Head, again, is another one of these phreatomagmatic centers. So this is the view from Mount Eden. Someone's gone and written high and boulders down in the bottom. But again, it's dated at about 21,000 years. So it's still a relatively young system, but it's largely vegetated on the flanks. You can see there's not much in the way of exposure here. Again, kind of a classic problem. But this is truly an urban one, in that we have dense housing literally all around the volcano here. As far as we're aware, this is one of the few that are kind of truly just a Strombolian volcano. If there's phreatomagmatic start to it, it's not really well exposed in this system. Again, there are a lot of lava tubes and lava flows coming off of this that all the houses are built on. The last one is North Head. So again, this one's a bit unique. So here is the volcano itself, and you get the little suburb of Devonport built all the way up around it. This is the only example we're aware of in the field that's a Circean type of eruption. And again, what this means is that the eruption took place actually underwater. So as opposed to simply steam heating the groundwater in the substrate and then having a subaerial eruption, the initial phases of this were all underwater. Importantly, I guess historically for this site, I don't know if you can actually see it, there's a slightly different color here. The channel that comes into the harbor actually runs right next to North Head. And as a result, since the late 1800s, this has been a fortified site. And there are tunnels and battlements kind of stationed all around the the volcano here, and it's been used on and off for military purposes. Now it's more of a museum, but it still gives some good exposure. So you can see here some of the early fortifications dug out into this tuff ring. Now, the geology helps us here a little bit in that the tuff ring, again, forms this border here with the current water, and it's much more resistant to erosion than the scoria cone on top. So all of the embowelments and the tunnels are all through this phreatomagmatic phase, and then the buildings just sit on top of the scoria cone because you can't really just tunnel through that as easily.
Can I ask a question?
Yeah.
So, I'm having a hard time imagining the initial eruptions occurring underwater 21,000 years ago when sea level was probably 150 meters lower.
This one's about 85.
Oh.
So this one's a little bit older,
Gotcha.
87, I think.
So now you're back into a high stand.
Yeah.
Okay, I got you.
Yeah.
Never mind.
Yeah. Again, the same sort of story for the eruption of the Strombolian deposit compared to the phreatomagmatic deposit. Again, the big difference being that we start off with the system being underwater. And again, it's all about the system drying out through time. What was proposed for this particular eruption is that the buildup of the tuff ring margins essentially isolated the vent area from the seawater and allowed it eventually to build up to more of a subaerial style eruption. But again, it's still largely dependent on the drying out of this particular vent, which then allowed it to transition to that Strombolian phase for the last gas. But very similar model as to what we were looking at for the phreatomagmatic eruption. Again, same problems looking at the scoria cone here. I don't think you can even really see it, but there's not a lot to work with in terms of the scoria cone, simply because it's highly oxidized and it's all buried in dense vegetation or museum. Either case, they don't really want you digging into it. So, what are the objectives here? The primary model for these systems that have been transitioning from phreatomagmatic behavior to this, I'll say magmatic, but it's just a drier system. It is essentially related to changes in the amount of water in that vent. So it says, all right, well, everything else essentially remains constant, and we're just drying out the system. So what I want to look at is whether or not we can change that around a little bit and say, well, what happens if we instead envision changes in how much magma or how fast that magma is actually coming up to the surface? And can that change over the course of the eruption and actually lead then to a change in the eruptive style? So it's not necessarily just that we're drying out the vent, we're actually changing how that magma is coming up near the surface. This is just a slightly different view. Here's again the volcanic field, and all I wanted to point out with this is this relationship to water. So again, obviously the blue is all submarine, but the brown here is everything from 0 to 30 meters above sea level. And again, that encompasses a lot of the greater Auckland area. So we have a lot of potential for having future phreatomagmatic eruptions throughout our existing volcanic field here. All right, so the basic assumption here is looking at groundmass crystallization, and that we can use groundmass crystallization as a proxy for the amount of undercooling or the rate of cooling in this particular system. Now this model has been applied to andesitic style eruptions, either Plinian or dome building eruptions, and the idea is that slow ascent tends to lock in this case, a low porosity and high crystallinity. And then we look at fast ascent rates, and in this case we've got fast undercooling, giving us low crystallinity. The same application's been, as I said, applied to domes, and the general correlation is that fast cooling gives us low crystallinity, slow cooling gives us high crystallinity. And so what I want to look at is whether or not we can actually use crystallinity as a proxy for how much or how fast that magma is coming up, and if we can see a correlation between that and the different eruption styles. All right, so what am I actually going to do then is look at the groundmass crystallinity through a bunch of these different eruptions, and also look at sulfur and chlorine as proxies for degassing, to see if we can see a correlation between the degassing of the magma system, and how this ground mass is crystallizing. We'll focus on the 4 volcanic centers that we've talked about, so 2 phreatomagmatic and 2 of this kind of Strombolian magmatic style. So for ground mass crystallinity, I'm going to use a slightly different approach, and this is all based around using X-ray diffraction. And the basic idea here is that X-ray diffraction is commonly used in the geosciences for looking at mineral phases. It's a mineralogical tool. And you get a signal return through an X-ray diffractometer based off of using Bragg's law, and the idea that what we're seeing is mineral structure reflected within our diffraction patterns. However, there's also a component here that's associated with an amorphous phase. So these peaks give us what's referred to as long range order. The amorphous component is what's referred to as short range order within this diffraction pattern. And we can actually go through and try to quantify this amorphous component in this diffraction signature. So if we break this up into its 2 components, we start off with something that's 100% crystalline or purely crystalline, and you have several different mineral phases that give you your diffraction patterns. You add in an amorphous component where you have this short range order, so you get what I'll refer to as this broad amorphous hump here for glass. And if you add those together, then the diffraction pattern you get is simply a combination of these 2. So we can actually back out the proportions of the crystalline amorphous components, simply looking at the integrated count rates associated with the amorphous component and the crystalline components. And just looking at the ratio then, if it's a ratio of amorphous over crystalline plus amorphous, it's just the inverse of crystallinity. And so we can get at magmatic crystallinity simply by looking at the diffraction patterns. To do this a little more rigorously, we've gone through and actually created a statistical software that takes our diffraction pattern and models it into its 3 base components, being some sort of a background, the amorphous component, and the crystalline component. Again, the output here is simply a ratio of the amorphous material to amorphous plus crystalline. So this allows us then, once we have a calibration curve to go along with this, we can calculate an actual crystallinity for these materials to within about 3 to 5%. The advantage of this approach over going through and looking at a thin section and doing things like point counting is that X-ray diffraction will pick up crystalline materials down to a few microns. So we can get a lot of those fine microlights that you probably don't want to have to go through and do point counting for. Also, it's a bulk approach, right? It allows us to look at a 3-dimensional block of material, crush it up, and analyze that whole sample, rather than relying on a 2-dimensional slice of that rock and hoping that that's a representative piece. So there are advantages. The disadvantages are it's a bulk analysis, and anyone who's done bulk rock analysis knows that there are a lot of issues that come along with that. You have to deal with alteration and a lot of other potential complications that you don't have when you're doing thin section work. So these are the sorts of materials we're looking at. Here's one from Moto Korea, from that upper scoria unit. And you can see it looks more like a typical scoria class, right? We've got a lot of large vesicles in it. It's got a lot of parts coming up and off of it. The phreatomagmatic material, again, as is typically seen for this material, is a bit more round or blocky looking. In some of it, we see that there are vesicles that are slightly filled with zeolite. Again, this is one of the complications to this, technique. And you also see in some of the clasts, you have a light brown glassy rim on this compared to the interior of the class below. But what this approach allows us to do is take each individual class, crush it up, and get a crystallinity for that given sample. And it allows us to do a population study, essentially, of the crystallinities, rather than having a single crystallinity representative of that particular sample. So backscatter imaging, again, just looking at some of the variations in the ground mass textures. You can see up here we've got a fairly glassy ground mass, some nice circular vesicles, some little pyroxenes popping up, a few iron titanium oxides. So this would represent a fairly glassy sample, and you can see we increasing crystallinity here, increasing more and more crystals there, and finally a much higher crystallinity here for this particular Mount Eden sample. So we get a lot of variety in texture and mineralogy that's showing up. I haven't focused at all on what the minerals actually are. In terms of quantifying the crystallinity, it's not really important. We know there's a lot of olivine, a lot of pyroxene. In some of these samples, we get nepheline showing up. We get some plagioclase showing up. But again, for bulk crystallinity measurements, I don't care. I just want to classify how much is crystal and how much is glass. Okay, so we're going to take a look starting with Motochorea and flip through several different sequences here. And I've tried to put these in stratigraphic order. So the image up at the top, is that's that middle scoria unit. So it's kind of midway in that 20-meter thick sequence of phreatomagmatic deposits. So we'll look at the two phreatomagmatic surge deposits right below it, that unit, and then the stuff right above it. And then we'll look at that upper scoria unit just for comparison. So all of these are versus particle radius, so crystallinity versus radius, with the idea being larger particles should cool slower. And so if we're seeing post-eruptive crystallization, it takes a few seconds for these to cool as they're flying through the air. We will see an increase in the amount of crystallization. And you can see it's not pretty, but there is a broad increase in the overall crystallinity as a function of the particle size. So this is 5, again, that basal phreatomagmatic unit. And I should also say, in each subsequent image, I've simply switched to an outline here, and then the data points represent that particular unit. So this is 4. So these are these 2 lower phreatomagmatic units. You can see we have very high ground mass crystallinities for these. Everything's up above 60%. Okay, now we're into that middle scoria unit here. So that's this deposit here. And again, it's pretty crystallized, and it largely overlaps with that, with those lower phreatomagmatic deposits. Moving up, so that's the unit directly above it, and then the one above that. So for this sequence of 5 samples, we're only talking stratigraphically, something that's about that wide for those total of 5 samples. We don't see a lot of variation in the crystallinity here. It's all largely crystalline, greater than 60% for the most part. And again, we see that general increase through time, but no real distinctions in those systems. If we throw in the upper scoria unit, though, we do get a bit more of a coherent trend here. We lose a lot of that scatter. And we generally we're down at the lowest end of that crystallization kind of sequence. Instead of going from 60 to 90, we're all from 55 to about 65. Again, slightly increasing with particle size. All right. So that's kind of the overall sequence for Motochorea there. Now, we'll do the same thing for North Head. Again, remember, North Head is our Circean style eruption. So it starts off with this subaqueous eruption and theoretically builds up into this subaerial system through time. So what you see in the sequence and in the stratigraphy is that there's much less crustal material. There's almost none. It's all juvenile magma that's accumulating here in a big pile. Again, this is consistent with the idea we're not blowing out that crustal material, we're just erupting into a submarine environment. So here's the base of that sequence. And stepping up, slightly higher crystallinity is there. So we move from that kind of thick pile of basaltic material into something more similar to what we're seeing at Motochorea, where you've got these alternating finely bedded layers here. Again, a high proportion of juvenile material. You can see it's a wet deposit. Well, maybe you can see, but there are big balm sags that show up in this. You do get a few crustal pieces, that light block in there. But this was a very wet environment that this was erupting into. Again, so a couple deposits, just thin layers, just looking for some variation there. And then the last bit of this phreatomagmatic phase, again, it's still finely bedded, but it's almost purely scoria. It comes apart pretty easily, but it's not the scoria cone at top. It's still in this wet phase, and you can see that they've carved it out again for these tunnels. But again, not a big variation in crystallinity. But when we put these two together, we do see a significant difference between the phreatomagmatic system at Motocrea versus that at North Head. So again, this is our subaerial eruption, again, water rock interaction in the substrate versus the submarine eruption that builds up to a subaerial system. Okay, so if we compare these two, and we'll break it up into Circean and phreatomagmatic. The Circean style deposit, one of the things, it's not just that it's lower, it's also we see much less variation. Now, there are a couple of potential explanations for this less variation. One, it could be simply a function of alteration. It could be that the Circean material has less alteration products. I mean, in the phreatomagmatic material at Motocrea, the student went through a lot of work to go through it and clean these materials up, but there's still some of these zeolites that sneak through. The other potential is that this could simply reflect less mixing at the vent, or less insulation of the clasts. So mixing at the vent is not something we really think about much. We think about these each being their own eruptions, but it can actually be quite problematic. So this is a video from one of the PhD students at Auckland, who's working in Vanuatu at Etna. So it's a Strombolian style eruption, but what I want you to see when we play this, and I'll start this going, maybe, is that when these clasts erupt up, so they're coming up out of this vent, they land up on the sides, they roll back down, and then the next big blast remobilizes this material. So we actually have this cycle of mixing these materials in the vent. And when this happens, this material, it comes out hot, cools a little bit, we get some crystallization occurring, comes back down into a hot vent, and then gets kicked out again. And so this repeated cycle of heating and cooling actually allows you to prolong that period of crystallization. Now, obviously not all of the materials go through this, but this is a very simple process to create a lot of heterogeneity when you start looking at individual clasts, trying to understand the processes involved. So we can have something like that affecting it. We could have alteration. The slight increase in the particle size for both the eruptions is consistent with this minor post-fragmentation crystallization. So this is after we've created particles and while they're being air-cooled. We could also explain that lower ground mass crystallinity through more rapid quenching upon eruption. Now, we'll look at this in terms of the volatiles here shortly, but the idea is that if we bring that material up quickly, it has less time to actually interact with groundwater. So it's cooling and crystallizing as it's ascending up from wherever it's being stored, but then it's being quenched in that submarine environment rather than a slower ascending magma that's interacting with groundwater and causing our phreatomagmatic eruptions. Now, I should have stopped there. But we decided to also look at these two magmatic systems as well. So this is combining Mount Eden and Rangitoto. Mount Eden here is in blue, Rangitoto is in red, and you can see that they look to largely overlap. A couple points I want to make about these is that in both cases these are largely bimodal. They've got one population that sits up high and another one, a much smaller one that sits down low. But again, if we treat this as a population, we can look at how this Strombolian phase compares to, in particular, how it compares to that, remember that last stage of the Motocrea eruption that had the low and low variation crystallinity in it. So if we look at treat it as averages and as a population, for that Motocrea sample, that transitioning to the Strombolian phase there, you get a ground mass crystallinity of about 62%, again with very low variation. Rangitoto and Mount Eden, we get higher variations. Again, some of this could be due to the recycling processes, but our averages are still right around kind of 60 to 65%. Now, the important part here is that this is about 10 to 20% lower on average than the phreatomagmatic phases of that Monocaria eruption. So we get the consistency between the Strombolian eruptions, the lower overall crystallinity compared to phreatomagmatic phases. So if we look at the phreatomagmatic versus the Strombolian style here, again, if we're working on the assumption that maybe this is tied to changing magmatic dynamics, the slower ascent rate resulting in higher crystallinity, again, may promote this magma-water interaction. But this would also apply a faster ascent rate for the Circean style eruption compared to the Strombolian style eruptions. So we can kind of order them in terms of their ascent rate and cooling based on the amount of ground mass crystallization. Now, the other part of this story is looking at the glass chemistry. And again, the idea here is looking at, in particular, sulfur and chlorine, because they're easy to measure. Now, really, when we talk about magmatic degassing, everyone's interested in water. But water is a real pain to analyze. And you can't do it as a population. So, colored here, we've got Monocaria in red, North Head in orange, Mount Eden in green, and Rangitoto here in blue. And what I want you to see, I've got two different types of materials plotted up here. The open symbols represent the ground mass glass. So this is equivalent to what we were analyzing for the ground mass crystallinity. The closed symbols represent melt inclusions. So melt inclusions for us record the pre-degassing melt compositions. So this should tell us what these compositions had prior to any sort of later stage degassing. If we put some very basic arrows on this to help out here. So this shows us kind of the maximum melt inclusion composition going down to kind of an average ground mass composition. What we're primarily interested in here is the loss of sulfur. Chlorine, it's sticky. It works like a trace element. It doesn't really degas much. But sulfur tends to degas at a very late stage of volcanic eruptions. So you can see the melt inclusions here at Monocaria almost completely overlap the range in the ground mass glass. All right, so again, this is our phreatomagmatic eruption. If we go to North Head, where it's erupting in a submarine environment, you see we have, again, fairly high starting sulfur concentrations, but the ground mass now much more consistent, but also significantly lower. All right, and then we go to our Strombolian style eruptions, again, relatively high starting sulfur concentrations, but essentially no sulfur there in the ground mass, or very, very little. So we can look at this in terms of amount of degassing, and we can say, all right, well, sulfur hasn't degassed here, some here, almost all of it there. Now, this is problematic in that this is different from what we were just describing in terms of the ground mass crystallization. The end result of this is that the degassing of the sulfur is telling us a different story than what we're getting from the ground mass crystallization. So in terms of, and this is more sense what I was just more or less what I was just talking about, the Strombolian eruptions show the greatest sulfur degassing, followed by the Circean and phreatomagmatic. Again, this makes sense in that the subaerial eruption should have the most amount of sulfur loss. It's subaerial, it's slowly cooling in the air. We would expect the ground mass to be completely degassed, and that is what we see. All right. The phreatomagmatic makes sense again. It's quenched before significant sulfur loss, so we don't see any sulfur degassing. And the Circean style eruption, again, we see it erupting and quenching into a subaqueous environment, so we'd expect to have something intermediate there. But again, it's a different story than what we're seeing from the ground mass crystallization. So if we put these two together, what I'm proposing is that they're actually telling us different parts of this shallow ascent and degassing. The ground mass crystallization, rather than being driven by actual volatile loss, is simply an effect of thermal cooling. So this is kind of a shallow ascent crystallization, but not necessarily related to that sulfur degassing and that last gasp of cooling as things are being erupted. So the ground mass crystallization, the Circean eruption is our fastest cooling, the Strombolian is intermediate, and the phreatomagmatic is the slowest. I'm suggesting that this is telling us more about that ascent of magma up through from the shallow storage system to the surface, where you're getting cooling-induced crystallization. The sulfur degassing, I would argue then, is instead telling us about essentially a syneruptive quenching. So again, this is the last gasp of this system. So the phreatomagmatic, very little sulfur loss, rapid quenching. The Circeans, intermediate with subaqueous eruptions. And then again, our Strombolian is that slowest quenching of the sulfur. So the idea is that these are both telling us something about this shallow ascent and eruption. They're just not necessarily telling us the same thing. Now, I've got a couple minutes, so I wanted to show a comparison to some work we've been doing at Ambai in Vanuatu. So last July, I was part of a team that went out as a kind of post-eruption response, looking both at the petrology and the mineralogy of the eruptive products, particle size analysis, looking at the tephra deposits. Other teams were looking at the cultural aspects, that the impact on vegetation and on some of the villages. So this is one particular village we visited, and unfortunately while we were there the eruption actually started up again. So it was quite an interesting time, but you can see the damage to the houses. This is a village that had been evacuated quite a while before, and we were just checking in to see the state of it at the time. But this just shows an example of what it was like working for a few days there. This is 3 in the afternoon, flash photography bouncing off the ash falling on us. So we actually had quite a bit of ash come down in a short period of time there. But these are all, this is a phreatomagmatic eruption actually originating at the summit of the mountain, where there's also a large crater lake. So it was building up, again, this scoria cone and having phreatomagmatic eruptions up at the summit. Just some examples here. So this is a kava field here. Again, there was a group looking at impacts on crops, impact on housing. Now here's this is the same grassy lawn, 2 days, 1 day before, 1 day after. Just looking at the change in what the chickens are able to eat. And so, this particular example was really looking at the impacts. This is subsistence style living. And in fact, we were on the last plane off the island before they started evacuating the island. And so they did a whole island evacuation shortly after. But obviously there's a lot of concern in the Auckland area for this style of phreatomagmatic eruption and the sorts of hazards that we need to be concerned with. So there was a lot of work between the VMGD and the New Zealand research groups studying this eruption. While we were there, though, we were able to also look at an older phreatomagmatic deposit, again, along the coast. So this is slightly different from what we were looking at in the Auckland example, in that it actually starts out as a scoria cone. And we have a nice transect of the scoria cone, so using my shadow here. Right over here is actually the core of that scoria cone. And I don't know if you can see it or not, but you can actually see the scoria beds sloping away there from that core. And as you go back along the beach, you go up section. And as you go up section, you actually transition into a phreatomagmatic deposit. So this is the reverse of what we were just looking at, in that we have a scoria cone in the core going up into a phreatomagmatic deposit. Now there's some thick units in here that look to be maybe some hydrothermal explosions as well, before you transition into, again, these what I call proper phreatomagmatic surge deposits up at the top. So I've had a master's student this year looking at, again, groundmass crystallization and glass chemistry, transitioning from the scoria cone up through this deposit, looking for evidence of change. So same sort of approach here, groundmass crystallization, supported with the BSE imaging. And you can see that there's, again, a wide range in groundmass crystallization. This large amorphous component here, slightly less, basically none there. Now the difference with this system is that it's very, very sulfur poor. In fact, it doesn't matter what phase of the eruption we look at, almost all of the sulfur is below 100 parts per million. So it's almost all completely degassed. So one, we don't see a correlation to sulfur. That eliminates one of my problems. That's great. So we can just focus on the ground mass crystallization. But if we look at how this goes up sequence, so this is organized going up stratigraphy here. This is kind of the core of that scoria cone. So this is much more oxidized material. So it's not surprising that it's more crystalline, right? It's hot, it's sticking together. We're seeing a lot of oxidation of iron and just generally higher ground mass crystallization. And then here we transition into this, well, transition phase going from the Strombolian center up to the phreatomagmatic center. But again, overall we have this decrease in crystallization going from our Strombolian phase to our phreatomagmatic phase. Now, for those of you following, that's exactly the opposite of what we saw for Auckland. This is actually what I expected to see in Auckland. And we found it here, but we didn't find it in Auckland. So here we have high amounts of ground mass crystallization in the Strombolian phase, with slightly less there in the phreatomagmatic phase. And so the argument that my student Nathan's making for this is that, well, here you have a lot of subaerial cooling, slow ascent. Here you're having more rapid cooling associated with potential phreatomagmatic, magma-water interaction. We have a couple of units spread throughout here that have much higher crystallinities, and in particular that also have very high variations. And these match up with these units that we think to be these hydrothermal explosions. So these aren't necessarily tied to phreatomagmatic base surges or Strombolian activity, but tend to have more variation from, again, these mixing processes. What I guess I should say is that we can create a plausible model for any scenario. That's fun. And as long as we don't consider all the systems together, they're all justified. But I mean, in all seriousness, we can create models that are consistent with both the sulfur degassing and the ground mass crystallization. But it's not surprising that they may not give unique solutions, given the complexities that are actually involved with these eruptions. I mean, nothing I've talked about takes into account the physical changes in the system, the buildup of the tuffering, the movement of the vent locations. So there's a lot of other aspects that need to be considered. But it does give us some evidence in terms of what's going on with the eruptive system as a whole. The sulfur degassing really, especially in the Auckland volcanic field, really only seems to record this syneruptive process. It's not telling us a lot about what's going on as that magma is coming up to the surface. It's just telling us that last gasp of the story here. It seems to be the ground mass crystallization that actually tells us more about kind of the shallow ascent processes. But it's being able to combine these two that gives us a whole view into the system. All right, so I will go ahead and stop there.
All right, thanks, Mike. Are you open for questions?
Sure, why not?
Excellent.
Other things that can affect ground mass crystallization, such as where the lava flow is relative to the channel that it's going down, or any confinement that it's going down.
Yeah, there are a lot of processes that will affect it. For this particular study, we've really focused just on the tephra deposits to avoid some of that. Okay. We did actually have a student a couple years ago looking at changes in ground mass crystallization along a single lava flow. Okay. The bigger issue is changes in the melt composition. So you do see changes in the amount of ground mass crystallization as a function of alkalinity, for example. Okay. So for the Auckland volcanic field, most of the compositions are relatively similar, again, excluding that one at Rangitoto. So, as a whole, we can consider that as a system, but I would then hesitate when I start trying to compare that to things like ambi that have a very different chemistry.
Okay.
Yeah.
If I understood your introduction correctly, you said a lot of this was oriented, being funded in terms of humans' responses to volcanic activity in terms of, like, you termed it civil defense, I'll call it emergency responses.
Yeah.
How do you integrate all of this material into one of those plans?
Well, I don't, first off. I leave that to someone
How
else.
does someone else do it? I'm not going to let you off the hook.
The biggest challenge, and what we can try to do with this, is introduce the potential mechanisms for why the eruptions change. The Strombolian style eruption is going to have very different hazards associated to the phreatomagmatic phases, and that's one of the biggest issues, is that you get these base surges that come out, that have a lot of force behind them. They're going to be very different from stuff raining down. And so understanding why we're getting the phreatomagmatic material, or when it can change that Strombolian style eruption, is really what we're trying to address with this. And so, we're trying to just look at the mechanisms a little bit differently.
And where you should live and not live.
Well, people are going to live where there's land. I mean, the problem with Auckland is that it's got seas on both sides. It's a very narrow strip, so there's not a lot of room to expand. So people are going to build wherever they can, and the land prices are quite high as a result. It's just understanding how we can understand what's driving the changes in the eruptions, so that people can plan better for how to look for evacuations.
Thank you.
It seems like maybe some of the answer could come from quantifying the ascent rates. Seems like that would have pretty big implications to hazards.
Yeah, and that's where a lot of this is trying. We have a lot of different approaches that we're trying to address ascent rate. Mm-hmm. So this started for me trying to get to ascent rate, looking at how the groundmass is crystallizing. Mm-hmm. We've got a PhD student who's actually working on Rangitoto, looking at how volatiles are degassing out of melt channels and crystals to get a ascent rate, more from, but those are more kind of from shallow storage or even deeper up to the surface. But there was another study that came out last year looking at diffusion of trace elements and hydrogen in olivine crystals. Again, all trying to get at this ascent rate process. It's very, very poorly constrained, and it's really hard to do well. Yeah. So there are a lot of kind of proxies being used. Sure. It's days to hours to months.
Right, and that's what the civil defense is going to be.
That's what they're most interested in, is how long do they really have?
Right, once it starts.
Yeah.
Well, my question it has to do with the evolution or the composition of the magma itself that's coming up. As you went back in history for a ways all the way to recent times, and you went from where there was more of the shield type flowing lavas to those that are just getting airborne. It would be, are these more silicic because of depletion of your gabbroic content and going from gabbroic to andesitic to dacitic?
There's no overall trend in the chemistry. So these are all basaltic. It's what's referred to as a monogenetic field. So each one gets treated as its own eruption, it's its own entity. But over the long term of the field, there's no systematic change. Now, in individual eruptions, now that people are trying to look at individual eruptions in more detail, they are starting to see some chemical variations that suggest that the source might be changing as a result of depletion in small packages. Motochrea is one actually that shows some variation from the start to the end of the eruption in terms of the source composition. But these get into the really fine details of the mantle source. And it's not clear that that's telling us a lot about how things are, what's actually going on up at the surface. But yeah, so individual volcanoes will have some chemical variation. Not all of them do, some of them do, but nothing widespread over the field. I mean, from the same regards, there's no obvious controls on where the magmas are popping up either. or where the volcanoes are popping up, and that's why we have to consider all of the different potential options for understanding these eruptive centers. There's no fault systems that everything seems to be aligned along. So it's very hard to predict kind of what style of eruption or where the next eruptions will likely occur.
Okay.
So what's the youngest?
500 years. So that's Rangitoto, so that's that shield volcano. So it's a little disconcerting that the youngest is also the one that's volumetrically the largest and different from everything else. Makes it very hard to start thinking about, well, what's going to happen next then? If you consider the other 51, it's fine, they're all about the same. But this 52 is different.
Yeah.
So.
And in terms of detecting seismic activity under the whole field, is it pretty highly monitored?
Surprisingly, it's not highly monitored. There are seismic stations kind of that puts them out at Rangitoto, and there's some around the city as well. But it's hard to monitor an entire volcanic field.
Yeah.
With a single volcano, yeah, you can put seismometers kind of all around it, but it's harder to do something like that field as a whole. Yeah.
Is there any effect that the city existing there, just the weight of buildings, etc., could cause any subsidence, any pressure on the overall magmatic field in any sense?
I don't think it would have much an effect on the volcanic field as a whole, just because of the city itself would be distributed over the entire volcanic field in both north and south of that as well. You worry about things like groundwater extraction, but when you live that close to water, everything's saturated anyway.
Yeah.
Any other questions?
That's it. Thank you so much, Mike. Mario, did you want to?
Oh yeah, the student club wanted to.
I'm wondering why it's not that flower.
Oh yeah, the student geology club wanted to.
And environmental science.
Oh yeah, and environmental science.
Thank you. I will make good use of it.
There we go. All right. Well, thank you again, Mike.